Okay, so this is going to be a special lecture where we're going to talk about molecular orbital theory. Now, normally in our class, we would cover this pretty in-depthly, but it's one of the more complicated topics, and it's definitely a challenge. And so we're going to just touch on it to a lighter degree this semester than I normally would do, because I know that it's kind of been a challenge as we've gone to this remote situation. Now, molecular orbital theory is similar to what we were talking about with hybridization, but it's to a much larger degree. And so what happens with molecular orbital theory and the way hybridization kind of used our Lewis theory to expand on it to come up with our molecular shapes, orbital theory is going back to Schrodinger's wave equation. Now, Schrodinger's wave equation is talking about the probability of where electrons are and how electrons move and travel. So what it does is it's looking for a set of molecular orbitals. So when the molecule is made, it's trying to find out some regions where these electrons are more likely to exist. So in practice, we don't actually solve these equations, we just come up with these very good estimates of them. We start off with where those orbitals kind of look like, and then we keep testing and tweaking until the energy of the orbital is minimized, and we end up with those molecular orbital values. So we kind of keep solving and adjusting these equations over and over and over again until we get the best possible answer. Now, the difference between molecular orbital theories versus all of those other theories that we've talked about is that the electrons, instead of being assigned to just one atom, they belong to the whole molecule. And so the orbitals, they belong to the whole molecule. So in a way, it's kind of like what resonance was trying to accomplish. Resonance was trying to take one molecule and show it in many different ways as those electrons spend less time just between those two atoms and spread themselves out. Molecular orbital theory is if we take all of those electrons and spread them out throughout the entire molecule. And so this is that delocalization impact. So molecular orbital theory is the simplest one, is that we start by taking those atomic orbitals and we add them together. And so this is called the linear combination ones. Once we have them, we decide whether they are going to work together. So whether those Schrodinger's equations are going to constructively form or destructively form. This is when they're going to work against each other. And so we can use those to build the shapes of our molecular orbitals. So inside our combinations, we basically get a bonding orbital where these orbitals are going to be constructively interfering with each other. That means they're working together. And they have less energy than their original atomic ones. On the other hand, we can have wave functions where they're going to be destructive. And those interactions are going to give us what we call antibonding orbitals, where the molecular orbitals have more energy than the atomic ones. Now, that doesn't mean that they don't exist. It just means that they have a higher energy than if they were in their atomic ones by themselves. Now, how you can tell the difference between our bonding and our antibonding is that our bonding is going to be sigma or pi, depending on which type they are. Sigma is going to be the ones directly in line between the atoms, or the nuclei. Pi are going to be the ones that go above and below, or be in front or behind. And they're shown just with the symbol. They don't have this star thing. So these stars over here, that's our antibonding sign. And the difference between the antibonding and the bonding is that bonding, most of the electron density where those electrons exist is between the nuclei. On the other one, the antibonding ones, most of the electron density is going to be outside the nuclei. So it's not going to be between them. It's going to be on the opposite sides. And basically where they meet is between them. So this is an example of two interactions between our 1s orbitals, right, which would look like these spheres. When they constructively work together, they form this overall one, which is bonding. And you can see that the electron density, there's a lot of it right here between the nuclei. The antibonding one looks like this up above. We have one side that's positive, we have one side that's negative, but those two are not working together. They're working against each other. And so a lot of their electron density isn't between, it's spread out on the back sides. So the part to remember is that electrons in bonding orbitals are good. They're stabilizing us. And that's because those bonding orbitals have lower energy. So the more electrons we have in bonding orbitals, the more stable we're going to be. Electrons in antibonding orbitals are destabilizing. It's because they have higher energies. So electrons in the antibonding kind of cancel out electrons in the bonding. And so we're trying to balance between those two. The more that we have in the bonding, the stronger those bonds are going to be. The more that we have in the antibonding, the weaker those bonds are going to be. So our antibonding is going to be greater than, our bonding ones are going to be less than. You can kind of see those changes here. So when we're looking at our molecular orbitals and we want to know whether or not those bonds are going to exist or what kind of bond order, we're really trying to compare the number of bonding electrons minus the number of antibonding electrons, and then we divide it by 2. So if we have the same number of bonding electrons and antibonding electrons, let's say that there was 3 in each, we'd have a bond order of 0, and it means that our bond shouldn't occur. This means that it's an unstable form compared to the individual atoms. It just means that there's no benefit in us forming those molecular orbitals compared to them being apart. If we're negative, which actually can't really happen, then we definitely aren't going to form a bond. The higher the bond order, the stronger that bond is going to be and the shorter that bond is going to be. And so we're going to do this with all of our valence electrons, is we'll look at where they're assigned as either bonding or antibonding. So this is the bond between 2 hydrogen atoms. So the side ones are our atoms before bonding. And this center point, this is going to be our molecular orbital. So this is going to be the orbitals that form if there's a bond. Now, however many orbitals that we have from the left and the right, we have to have the same number in the middle. So you can see that we had 1 orbital from here and 1 orbital from here. And so that means that we should have 2 orbitals in the middle. One of them is going to be bonding, which is this one down here at the bottom. The other one is going to be antibonding, which is up on the top. So in this example, if we want to find our bond order, we should have 2 electrons in the bonding minus no electrons in the antibonding divided by 2. And so we have a bond order of 1. Lithium behaves in a similar way. We have 1 electron for its valence, 1 electron in its valence. You can see that their atomic orbitals are listed here, the 2s. And so when we mix those two together, we should be making a sigma bond because it's only our first bond between them. And it's going to be our sigma 2s. And so we have our bonding and we have our antibonding. When our p orbitals start to interact, you can kind of see these are what our atomic ones look like here. We can see what a bonding one looks like, where there's the sharing between the nuclei, versus our antibonding, where the majority of our sharing is happening outside the nuclei. So this is our sigma because they're placed along the axis. This is our pi. You can see the difference between our bonding and our antibonding. These are the top and bottom ones compared to the front and back. And so we can get more complex molecular orbitals. You can see that for our s orbitals, we should have 1 sigma bonding, 1 sigma antibonding. For our 2p, we have 3 orbitals from this side and 3 over here, so we should have a total of 6 in the middle. We're going to get the 2 is going to be our pi, and the solar one is always going to be our sigma. And that's going to be true for all of our molecular orbitals. So if you needed to label them, what you're looking for is you're looking for the one that's by itself is going to be our sigma, the ones that are going to be 2 options, that's going to be our pi. And that's because we have 2 orientations for the pi, as you can see here, and we only have 1 orientation for the sigma. Now, normally we would cover the difference between these two, but pretty much some molecules will favor this arrangement where our pi is lower energy than our sigma. Other ones will favor this arrangement where our sigma is lower than our pi. It really has to deal with their electron densities and, their electron negativities and how the energies of their different sigma versus their pi bonds that they can form. We're not going to worry about that for this semester, right? But that is something that you can do. If you're interested about that, we can always go over this during office hours. And so the part to remember that as you fill it in is that you want to take all of the electrons from the left-hand side and all of the electrons from the right-hand side, and you need to move them to the middle. So your number of electrons from the outside should equal the number of electrons in the shared. Your number of orbitals are also equal. So the ones on the outside also equal the number of orbitals on the inside. And so just to fill this in really quick, if we had oxygen over here, and let's say that we had something like fluorine on this side, our oxygen, I'm going to do that one in with our red color, oxygen should have 6 valence electrons. So we should have 1, 2, 3, 4, 5, 6. Our fluorine, which I'm going to use this blue for, our fluorine should have 7 valence electrons. So as we start to fill them, I'm going to put those in to the middle part. So we can take our oxygen and our fluorine ones and we can mix them together to form our molecular orbitals, and the molecular one's going to be the purple. And so down here at the bottom, we should have 4. So 1, 2, 3, 4. And so our 2s is filled. And then we can move up to this next section up on top. So we should have a total of 4 from the oxygen, 5 from the fluorine, so we should have 9. So we should be 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see that as we fill in, we follow the same rules that we've always done for our orbital diagrams. We're filling from the lowest energy to the top. We're following the rule where we're spreading them out before we pair them. And so as we go through this, you can see now that our bond order, we have a total of 2, 4, 6, 8. So we have a total of 8 bonding electrons. Minus we have 2 plus another 3 anti-bonding electrons. You can see the little stars that they have here. So that's 5 anti-bonding electrons. And we're going to divide that by 2. So that's 8 minus 5. That becomes 3. 3 divided by 2 becomes 1.5. So our bond between O and F has a bond order of 1.5. And that's what you would do for your molecular orbital diagrams. The reason why this came up was that they are helpful in us talking about whether things are going to be magnetic or paramagnetic. And so how this showed up was oxygen. O2, when we looked at the diagrams without our molecular orbitals, we would have thought that it looked like they were all paired up. It looks like we should have something that looks like this inside of their pairing. So it looks like everything should be paired and it should become a diamagnetic one. Oh, sorry. We are thinking that basically it shouldn't interact with our magnetism because everything should be paired up. Magnetic materials, though, they are supposed to have unpaired electrons. And so if you pour oxygen between magnets, we start to see them get stuck. They are attracted there. And so that means that there must be some unpaired electrons in there, but it doesn't make any sense from our Lewis orbitals and the Lewis theory. So when you fill in your diagram for it, nope, where's my oxygen one? If we want to compare our oxygen orbitals, you can see that we would have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see now that we have 2 unpaired electrons. And that is why we can finally predict correctly why oxygen is paramagnetic, because it does have the unpaired ones, which isn't something that we see in valence bond theory or the Lewis theory. And so that was kind of what drove that process forward. What you want to know is we should be able to calculate bond order. So if I was to give you a diagram, we should be able to calculate the bond order from it. We should have an understanding of the difference between antibonding versus bonding. And then we should be able to eventually fill in the middle piece if I was to give it to you. So I would always give you this section so you don't have to remember how they're arranged, but we should be able to piece them together based on their the number of electrons, or sorry, from the electrons. And so once we know that, then we know which one has our shortest bond length because we can look at our bond order. We could also know whether a molecule should exist or not. And so you would just want to be working through on that information. We'll go over this a little bit more tomorrow. This will only be lightly on exam number 3, and then it can come up again for exam number 4 you'll find. All right.